Hello, good evening. Thank you for inviting me to give this keynote address at IEEE IRI, Information Reuse and Integration for Data Science. And the conference was supposed to be held in Las Vegas, August 11th, 12th, and 13th. And it's now being held virtually. And I'm really honored to give this keynote presentation. And this video is being recorded on August 4th, 2020, and my talk will be on August 12th, 2020. So I have been attending IRI since 2009, I believe, when I gave a keynote address. So I'm really honored to attend IRI again virtually to give this keynote address. So I will share my screen. Okay, so my talk is going to be on, SecAI, integrating cybersecurity and artificial intelligence with applications in Internet of Transportation and infrastructures. And I have around 55 minutes for this talk, so hopefully I'll talk for about 45, 50 minutes, and then we'll have some time for questions. So, okay, so my part one of this talk is going to be on SecAI, security and AI. And the topics include big data security and privacy, privacy-aware quantified self, data science, machine learning AI for cybersecurity applications, and securing data science ML AI techniques. Then part two is going to be on security and privacy for Internet of Transportation and infrastructures. And part three is going to combine part one and part two, and that's going to be on applications of SecAI for Internet of Transportation and infrastructures. I'd like to thank a number of our sponsors for funding various aspects of this research, as well as my colleagues, Professors Alvaro Cardenas, Murad Kantajalu, Latifa Khan, and our former PhD student, he's now Dr. Raul Quinones, and our project coordinator, Ms. Rhonda Walls. Okay, so SecAI, integrating cybersecurity, AI, ML, data science. So I want to give some motivation, right? Integrating cybersecurity and AI/data science. So goes back quite a while on data mining, security, and privacy. So I introduced the idea of the privacy violations that could happen due to data mining, as well as data mining for security applications back in 1996. I believe it was in July 1996 when I was at the MITRE Corporation. I gave a keynote address, IEEE 11.3 in Como, Italy. And I gave a version of the talk later at the Pacific Asia Knowledge Discovery in Databases, and that was in Melbourne, Australia in 1998, and then published, I would call a landmark paper. I'll explain why. While I was at NSF, National Science Foundation, in 2002, and that spawned a new area of research. I call it landmark because when you are a program director at NSF, and when you write a position paper, you know, that gets a lot of citations. And also because you are responsible for funding, it also it also gives rise to a new area of research. So the idea behind it, right, so the whole area of privacy preserving data mining. Now that particular aspect, the research was initially started by IBM Almaden Research Center, Rakesh Agrawal and his team, and also Chris Clifton at MITRE Corporation was also doing some work related to that area. And so essentially what you do is take the original data X, add noise, so it becomes X prime. So you perturb the data or randomize the data, and then you have a modified data mining process. And then you get the final result, and the end result should be more or less the same, right? Otherwise, there's no point in doing data mining. And so when I joined UT Dallas in October 2004, my first PhD student, a lady, Dr. Li Liu, and we co-supervised jointly with Dr. Murad Kantarjalu, my colleague, and we focused on privacy-preserving decision trees and also the perturbation method, and that was between 2005 and 2008. And so more recently with big data, right, data mining, security, and privacy is exacerbated because you now collect lots and lots of data. And so we hosted an NSF workshop on big data, security, and privacy in September 2014. Myself, Elisa Bertino, and Murad Kantarjalu, and Chris Clifton was the person at NSF at the time who sponsored this workshop. And we presented the results to an interagency working group in February 2015. And I believe that this was about the beginnings of a privacy-focused effort among the various agencies. Okay, so this is my paper, and also the data mining, national security and privacy, and some of our work on privacy-preserving decision trees. Okay, so what did we do at that workshop? So we focused on big data, security, and privacy. So again, due to technological advances, right, and novel applications, it's now possible to capture, process, analyze large amounts of data, right? It could be used for finance, for healthcare, for a number of tasks, also for security-related tasks. So such tasks could include like user authentication, access control, anomaly detection. So you need insider threat detection. So data mining or data analytics has been applied for all these tasks. By analyzing the integrated data collected on the web, you can identify connections and relationships among individuals, help with homeland protection, disease outbreaks, especially now with COVID-19. So collected data, even if anonymized, you can remove identifiers, but when you link the data together, you could re-identify the individual, right? So security tasks such as authentication and access control may require detailed information about the users, such as multi-factor authentication. And if this information is misused or stolen, it can lead to really bad situations like privacy breaches and so on. So the workshop focused on secure data access control, as well as privacy enhanced techniques and big data analytics for cybersecurity. So from this workshop, we carried out an investigation, UT Dallas and Purdue, on privacy-aware quantified self. That is the, psychologists, sociologists, they have gotten together and come up with this quantified self movement, right? You want to gather all sorts of information about people to help humanity, right? Collected from wearable devices, smartphones. You analyze to give guidance to users, improve their health, personal life habits, lifestyle habits, and the data also being shared with other service providers, cloud-based services, bringing potential benefits to users. But such data collection and sharing, often carried out without the user's knowledge, can bring grave danger, right? Privacy violations, as well as some other bad consequences as well. So data collected by a device monitored glucose levels, right? It might be used by insurance companies to deny coverage, not only to you, but also to your relatives. So such privacy violations could easily get out of control if data collectors could aggregate all of the financial and health related data, tweets, Facebook activity, and so on, and purchase patterns. And this could result in lawsuits against data collectors and psychological problems and so on. So to address these growing challenges, we really need tools for privacy-aware quantified self applications. And so we did an investigation, and our results are published in ACM SACMAT 2018, myself, Murad, Elisa, Jonathan Bektash, and Maribel Fernandez. And so we had some very interesting ideas in that paper. Okay, so what we are saying is that policies should guide all of the process. So we are carrying our smartphone, right? Lots of data coming in, health, fitness, location, social media, image, videos, and other sources, and so on. And so you have data collection, data storage, data analytics, and data sharing. Some of the data, of course, stored in the cloud. It could be encrypted, and cloud-based services can provide various types of services. So anonymized data, encrypted shared data, providing results to queries. And this quantified self now becomes privacy-aware quantified self-manager, and that runs on a mobile device. Okay, so what we are saying that policies should guide the entire life cycle of the data. So that includes policy-aware, policy-based data collection, policy-based data storage, policy-based data analytics, and policy-based data sharing. So for instance, policy-aware data collection, storage, analytics, and sharing, as more data are collected, the storage on the device will not be sufficient to store all of the data, right? So we envision some data to be in the cloud and encrypted. Frequently accessed data could be on your smartphone, and less frequently accessed data could be in the cloud. Based on the access control policies, local applications running on the devices will be given access to some of the collected data via some query interface. In some cases, you don't have to sort of get daily data, like daily weight of a 20-year-old. You don't need that, right? For an older person, of course, like for a 60 or 70, 80-year-old person, you may want to monitor the daily data, daily blood glucose or blood pressure. But for a 20-year-old, you could do maybe monthly data and maybe blood pressure every week or something like that. In other cases, data has to be deleted. And again, you need deletion policies, right? Even if the data is deleted, how do you know the service provider is really deleting the data? We envision that data sharing and analytics will be carried out using the services running in the cloud. And based on different scenarios, some of that data could be sent without any modifications, like heart rate and so on, and some will be sent after sanitization. So again, policies are guiding throughout the process. And when I say policies, we don't want just toy policies, because we are computer scientists. When I say toy, T-O-Y, right? We want to work with policy experts. So in many of our applications, like with data sharing, we have like toy applications like children, right? I give you a secret, and provided you don't tell that secret with or share it with Tom or Mary, right? So we don't want those kinds of policies. So more recently, we have begun work with a policy expert at UT Dallas, Dr. Jennifer Holmes. She's actually the dean of our School of Economics, Policy, and Political Sciences. Okay, so hopefully we can come up with some more realistic policies. Okay, so now I'm going to move on to data science for cybersecurity applications, and in particular, big data stream classification. This is joint work with Professor Latif Khan. So what we are doing here is using past data to build classification models, right? And you predict the labels of future instances using the model, and it can help in decision making. So what do we do here? Big data streams. Data streams meaning continuously data is arriving, right? It could be telecom data or network traffic data or stock market data, continuous data. And it's very common in our connected digital world, right? Even healthcare data continuously arriving about a particular person, like heartbeats and so on. Massive amounts of data, so network traffic data. And we develop the classification models. And then test data comes in. If it's an attack, we block and quarantine. If not, benign traffic, we send it to the server. Okay, and then expert analysis and labeling. So what we have done, and it's joint work with my colleague, PhD students, postdocs, and also with University of Illinois Urbana-Champaign, Professor J.W. Hahn and his team. We started this work for NASA, and then we also did some work for the Air Force. Okay, so the whole idea is that we also, what is really unique about our work is that we can detect novel classes. That means it's not just a red class or a blue class, but we could have a highly novel purple class. And that's what we are detecting. Okay, so in order to do that, what we do is, because concepts are changing when you talk about streaming data, right? You don't have one concept. Concepts are arriving continuously. So what happens is that when these concepts arrive and when they are changing, we are building an ensemble of models, not just one model, ensemble. But over time, some of the models may be invalid. So we throw them away, and when the concepts change, we develop some new models. So we have an algorithm by which we can discard some of the, not just the old models, it may not, it could be old but still valid, but some models, you know, they may not be valid any longer, right? So we have models that are changing continuously. So that's really the challenge, and we published several papers. I've only listed one. And then we applied this to inside a threat detection. Inside a threat, again, there are people in agencies who are really bad people, but they pretend to be good people, right? So similarly, in our machines, networks and computers, there are bad processes, but they pretend to be good processes, so they may not be caught. And that's what we are trying to catch. So we've developed ensemble-based stream mining algorithms based on supervised learning as well as unsupervised learning. The result is a classifier that exhibits substantially increased classification accuracy. So we have compared our results with several others, and I'm going to cite a paper in the next chart. We have also designed and developed unsupervised ensembles. So our algorithms are based on support vector machines for supervised and graph-based techniques for unsupervised learning. So unsupervised learning, we also use compression to model common behavior sequences for better performance. This results in a classifier exhibiting a substantial increase in classification accuracy. The ensemble of classifiers allows the unsupervised approach to outperform the traditional static learning approaches. Okay, so this is our architecture. And so we have system calls, so we have modeled several behavior that we have captured. So again, the challenge is to extract the appropriate features, right? That's where you need the cybersecurity specialists to work with the machine learning experts. So you have KI chunks, right? And so you gather data from all of the chunks and you develop an ensemble of models, extract features, and then apply learning algorithms, either support vector machine or GBAD for unsupervised. And then we have an ensemble of models. Remember, streaming data. And then when the I plus 1th chunk arrives, you extract all the features and you select the features, and then you test. If it's an anomaly, then you flag it, right? So we've applied it successfully for insider threat detection. And it's with my PhD student. We had a professional programmer and some other PhD master's students and my colleagues. And so we published a number of papers, and I've listed one of them. Okay, so this is machine learning or data science for cybersecurity. So it could be insider threat, it could be malware detection, or it could be intrusion detection. It could be any one of the cybersecurity problems, okay? So now, more recently, the challenge is what happens if these machine learning, AI, data science techniques are attacked, right? Because these machine learning techniques could be used for healthcare, it could be used for what else? It could be used for anything, financial applications, and as I said, cybersecurity applications. If they are attacked, you cannot trust them, trust the results, because it could say that you have like diabetes when you really have cancer, and that could be disastrous, right? And so why would it happen? So the adversary is going to look at the algorithms we are using, the data we are using, and it's trying to thwart our algorithms and our data, or it's trying to thwart its behavior based on the algorithms and data that we are using. And so when that happens, right, it can remain anonymous. It may not get caught. So I'm going to explain in a minute. So adversarial machine learning, it's not concept drift, it's not online learning. Adversary adapts to avoid being detected. So it can learn from what we are doing, and then it can modify its behavior. It could happen during training time, like data poisoning, during testing time. So eventually it becomes a game between the adversary and us. Okay, so what happens here? Look, this is the support vector machine boundary, right? You saw the red squares are the bad guys, bad people. The blue circles are the good people. So you saw how these bad folks, right? What I showed you, the bad guys are coming, crossing the boundary and coming here so that they will not be detected. Okay, so that is what is happening, right? Because they have learned our behavior, our patterns, our algorithms, and so on. So we want to prevent that. So the number of types of attacks, and I don't have time to go through, and I'll list a paper in the next chart. And so you have free range attacks where adversary can move malicious data anywhere in this range. And then you also have targeted attack. The point here is that these are not just the only attacks. These are the attacks that we have examined. In reality, there could be hundreds and hundreds of attacks. And that's where some people are saying, okay, so you handle free range or some targeted attacks, but adversary can find another attack. Yes, all the adversary has to do is to find one way to get in, right? But for us, we've got to handle all the hundreds of ways the adversary can get in. And so that's impossible. So what I say is something is better than nothing. Okay, so look at this. So what we are doing is that this is the support vector machine boundary. The red crosses are the bad people and the green circles are the good folks, right? Good instances. And so what we are doing with some mathematical computations, we are moving this boundary line, dash line, to this blue line. Black dash line is the standard support vector machine classification boundary. And the blue line is the adversarial support vector machine classification boundary. And so we are trying to move, by moving it, look, the threat model, attacker modifies X to X prime, modified packet length by adding dummy bytes, okay, and add good word to spam email, add noise to the images. Anyway, it's moved. And you can see that before, some of these red crosses went in here and they would not be caught because all that it's going to catch is below this dash line. But now that we have moved this boundary here, some of the bad instances will be caught, right? So you can ask the question, this boundary line could be moved right here, but then it defeats the purpose because all the green instances will be detected as bad instances. And that's going to give us false positives. We don't want false positives, nor do we want false negatives. And we published, this is one of the early papers that we published. It was sponsored by the Army Research Office in the top data science conference, ACM CKDD. And so, the paper has all the details. And since then, we've done a lot more work, especially my colleague Murat and his our research scientist, Dr. Yan Zhao. They've done a lot of work on adversarial machine learning. Okay, so that's a challenge, right? How do you move this line, right? And that's where a lot of mathematical computations, and you need to get that right place to catch as many bad instances as possible. Okay, so now moving on to part 2, security and privacy for Internet of Transportation and critical infrastructures. This is joint work with Dr. Alvaro Cardenas, my colleague, and our joint student. Actually, it's mostly Alvaro's work, Dr. Cardenas. I am still learning. It's all about cyber-physical systems, so I'm really excited about this. We all know Internet of Things, right? We are living in a connected world, whether we are at home, whether we are at work, whether we are driving, whatever. Right home, we have a refrigerator connected to radios, connected to alarm clocks and lights and so on. But Internet of Things, also Internet of Transportation. For transportation applications, right, we have all these vehicles, the trains, and we have the roadworks and trucks, all connected to each other. Okay, so Internet of Transportation, IoT, Internet of Things has major implications in the transportation industry. Autonomous vehicles, AVs, aim at improving day-to-day activities, right? Such as delivering packages, improving traffic, transportation of goods. In the US, trucks alone carry, at least 63.3% of freight of goods. AVs are not limited to ground vehicles. You can have aerial vehicles like drones and airplanes, and sea vehicles like ships and boats, a wide range of applications. Levels of automation for AVs, they range from 0 to 5. 5 is fully automated, 0 is no automation, and we now only have a 2, level 2. And we'd like to have at least a level 4, or well, we want to have level 5, but interesting thing, aerial vehicles have a high automation at level 4. Companies are interested heavily in AVs. GM spent $728 million in R&D 2018 and $1 billion in 2019. It'll be interesting to get their actual numbers. While there is great potential in AVs and the improvements it can do to the transportation industries, again, major concern, security and privacy. What happens if these AVs are attacked? And how do you ensure the privacy? So our PhD student, or now is Dr. Raul Quinones, did some very interesting work. AVs evaluate their environment using a variety of sensors, cameras, GPS, inertial measurement units, LIDAR, radar, ultrasonic sensors, and so on. Previous research has shown that sensors are susceptible to malicious tampering. Example, IMU, inertial measurement units, are susceptible to sound waves, and GPS, global positioning systems receptors, are susceptible to spoofing signals. Vehicles should verify the veracity of signals, sensor signals, before acting on them. So here you have sensor-based, right? AVs rely on sensors to evaluate, interact with their environment. And then you have inherited issues like sensors are susceptible to GPS spoofing and transduction attacks, and so on, that manipulate the physical signals. Then you have the needed defenses, classical computing security, such as memory protection, cryptography, and authentication. While it's needed, it doesn't protect against these very specific types of attacks. And so no verification. Due to real-time constraints, AVs trust and act upon sensor data without any form of verification. So it has to be able to act very quickly. Okay, so what did we do? We came up with a physics-based anomaly detector, right? So this paper is accepted in the Usenet Security Conference, which is going to be, I think, this month, to build a reference monitor using physics-based anomaly, PBAD algorithm for ground and aerial AVs, vehicles. So physics means looking at the physical properties, right, of the system, right? So physical properties could be the velocity, the acceleration, and various other physical invariants. So algorithm will consist of 3 parts. We build a model offline of the AV's physical invariants, implementing an online tool to monitor expected and observed behavior to detect anomalies, and raising an alarm if significant residual difference exists between executions. So we have offline pre-processing, online verification, and then an anomaly detection. Okay, so what did we do? So physics-based, so what you see in the right-hand side, all the physical formulas and the equations that we used to develop the model. It was really the work of Dr. Cardenas and Dr. Quinones. Offline pre-processing, the AV's invariants are calculated using a well-known nonlinear model for aerial and ground vehicles. Accelerometer, gyroscope, magnetometer, sensor data on the XYZ axis is used for aerial vehicle positioning, and steering angle is used for the ground vehicle. Online stage, we used extended Kalman filters. It's not exactly machine learning, but we could enhance it with some machine learning. Kalman filter has been around for a very long time, used in control systems and so on. Is used to predict AV's physical behavior by estimating unknown parameters from noisy sensor input. Algorithm is divided into 2 sections, predicts and corrects the estimator before it is compared against the sensor data. Anomaly detection, we use a CUSUM, C-U-S-U-M algorithm, and that's also an existing algorithm, is then used to detect persistent attacks. An alarm is raised if the residual difference is larger than a predefined threshold. So the approach is, I won't call it straightforward, but it's a step-by-step approach, but it's quite complex because you've got to build this model and applying Kalman filter and so on. It's not really straightforward. Okay. So the physical implementation, I've got about, another 15 minutes, I believe. So aerial AV, Intel ready to fly RTF drones. So we had some aerial and ground. We didn't do the ships, right? Because we don't have water in in Texas. So, well, we have rivers and lakes and so on, but we don't have ocean. So anyway, aerial AVs, Intel ready-to-fly drone, controller, PX4 flight controller, focused on detecting GPS spoofing and gyroscope attacks. GPS attacks are detected after 0.2 seconds, while gyroscope attacks are detected after 1.5 seconds. Overhead introduced is just 5.433%. And that's for aerial. For ground, custom built on top of a Traxxas Ford Fiesta ST Rally chassis, controller, ROS kinetic cam, focused on detecting visual attacks on the camera, attacks detected after 0.1 seconds, and the overhead is less, 2.2501. Each threshold produces a probability of false alarms of approximately 2%. And so this is also the Usenex paper. So more recently I contributed and we submitted a paper for another conference. So we are waiting to hear the results. And so I'm really learning a lot. That's why I'm really excited about this particular field. Okay, so that's the security part. Now for the privacy, beyond the security of individual vehicles, the transportation sector could greatly benefit from a supporting infrastructure that allows communication between vehicles, motion sensors on lampposts, and surveillance cameras, right? To help identify traffic jams, reroute vehicles, increase vehicle safety. So without a doubt, we really need this technology, okay? But from the user's perspective, privacy concerns arise from all the information needed by such a system. So again, just like what I mentioned earlier, as we collect more and more information, right, the location of the person could lead to private information being exposed, such as vehicle identification and driving patterns. You don't want everyone to know, right, that you are driving erratically, right? So you don't want people to know, again, your location. Legislators, engineers, scientists should keep privacy concerns in mind as advances in IoT become more prominent in day-to-day activities. Whether we like it or not, IoT is here to stay. And we might as well make it secure, and we have to ensure that privacy of the individuals are ensured, because again, if it's not secure, it can cause really a chaotic situation. This will aid at improving the public perception, reduce hesitation from consumers, and increase the adoption rate of all these new technologies. So yes, security is important, because without security, you can have all kinds of accidents, but privacy is also equally important, because we have to protect the privacy of the individuals. Right, so that's part 2. Part 3, applications of SecAI, which is part 1, for Internet of Transportation and Infrastructures, which is part 2. Okay, so data science AI for transportation security. Internet of Transportation systems, we said, are subject to attack, right? Just like any other cyber-physical system. Streaming data is being collected from such systems, including autonomous, and in the future, yes, we are also going to have driverless vehicles. That's going to be really scary when all these driverless cars are going around, and what's going to happen, right? So now with COVID, I think, things might get delayed, but technology is still going to advance. As transportation systems go electric, we also need energy conservation. What happens if the transportation systems are attacked in the lonely highways or middle of the desert? I mean, you don't want to get stranded, right? Because what if happens if the energy management is messed up? Okay, so data science ML techniques are being applied to analyze the data. So the first question, can stream analytics, remember what I mentioned, stream analytics, because data is continuously being collected by these sensors, learning be applied to say that they are applying to financial data and telecom data? Can these techniques be applied to transportation data? Right, research in this area has already begun. We are seeing papers being published, but there's a lot more work to do. The main question is to understand the nature of the complex transportation data and adapt the stream analytics techniques and apply them on the massive amounts of heterogeneous sensor data being collected, right? Okay, so that's one, applying data science, AI for transportation security. Second, remember I mentioned adversarial machine learning? What happens if the AI techniques we are applying for transportation systems, right? Because to coordinate, to to do various kinds of operations, we will need AI for intelligent transportation systems, not just for security. We also need for automating, for AVs to coordinate their activities. We have planning systems, machine learning systems, or machine learning techniques, all of those techniques being applied. So what happens if these systems are attacked? So Internet of Transportation will depend heavily on data science, AI, ML techniques for various applications, including optimum directions, driving without a human in the loop, and many more. However, the adversary is learning our models, adversary is learning the data we are using, and it's going to try and thwart our behavior. Adversary will attempt to thwart the vehicle's learning process. Therefore, the learning algorithms, we've got to adapt, right, to the adversaries, learn about the adversaries' actions. So eventually, and I forgot to mention that earlier chart, it becomes like a game between us, who are the defenders, and the attackers, the adversary, right? It could be various types of games, right? It could be a zero-sum game, a Bayesian game, more recently Stackelberg games are being explored. So we need to understand the data is essential, right? Research on this topic is only beginning for transportation systems, but we are going to hear more and more about the machine learning techniques applied for transportation systems being attacked. Okay, remember I showed a picture earlier when we had our smartphones and all kinds of health data being collected? So the question I have is, can privacy-aware policy-based data management framework be used for the Internet of Transportation systems? So here we have, instead of a cell phone or a smartphone, we have a vehicle, a car, automobile, radar, GPS, cameras, LIDAR, ultrasonic sensors, all getting in here, and data collected, data stored, data analytics, and data sharing. And this data is going to, not all of the data can be in the car, right? Because you have only so much memory there. So some of the data going into cloud storage, and you have cloud-based services. Some may be encrypted, some may not. Anonymized data, encrypted sharing data, and get the results of queries. And so this now becomes privacy-aware, policy-based autonomous vehicles. What sort of policies do we need for data collection, data storage, and so on? So my colleague Alvaro, he has a project with our dean, Dr. Jennifer Holmes, to look at power grids in Colombia, the South American country Colombia. So Jennifer is looking at all the policies, and Alvaro is looking at some technologies. It's NSF funded project, so it's really interesting. Okay, so this is something, the future. Okay, now another thing I wanted to say was, what about trustworthy analytics, right? Very briefly. Can we apply this to Internet of Transportation? Trustworthy analytics, meaning computations over big data require massive computational resources. Let me check the time because I have, just a second. Oh. Okay, so, right, I still have, I know I rushed a little bit. I still have about 4 or 5 minutes. Okay, so what about trustworthy analytics? Computations over big data may require massive computational resources. Organizations, automobile companies may use a third-party service to outsource some computations. When a third-party server, like, we have the cloud and so on, is used for computation, data inherently becomes available in untrusted environments. So you can have man-in-the-middle attacks during data transmission or insider threat from adversaries at a third-party location. In these cases, data owners may need to protect their data and require cryptographic guarantees about data security and integrity. We are conducting research in secure encrypted stream data processing, both my colleagues, Dr. Latifa Khan and Murad Kantajalu, and using trustworthy analytics, and they are using the advancements in embedded hardware technology, such as Intel SGX to support trusted execution environment, and need to explore the applications to Internet of Transportation and infrastructures. We have not really looked into it. This is just, I'm just talking about it for the future. Can we use some trustworthy analytics, like for instance, the Intel SGX platform? How can we use it for data analytics? We have used it actually for data analytics, meaning there are SGX enclave memories. We execute highly critical data analytics techniques. So this could be secure, but there are some issues now with this SGX more recently. So we need to look into this further. So the enclave memories where it's performing data analytics, and we have other applications. SGX has got runtime library and then all the encrypted code. So this provides some security, although there are some issues that we are hearing about this, but I need to look into it further. But the challenge is, how can we use this, or can we use this sort of technology for trustworthy analytics for Internet of Transportation systems? Okay, so my last chart. Right, so what have we talked about? So part one, I talked about integrating security and AI, right? So developments in security and AI, integrating cybersecurity and artificial intelligence. And by AI, I also include data science and machine learning, and they are exploding. Applications, we can apply AI and data science for security. And I gave an example, insider threat detection. And we have done a lot of work. My colleague, Dr. Latifa Khan, and myself, we also wrote a book about 7-8 years ago called Data Mining Tools for Malware Detection or Malware Analysis. So we have applied AI, data mining, data science for malware analysis. We have applied it for insider threat detection and for intrusion detection, email worm detection, botnet detection. And okay, so that's what I talked about, streaming data, right? Stream data analytics for cybersecurity. The second part we talked was security for AI. That means the AI techniques, regardless of whether we are using it for cybersecurity or for healthcare or for financial applications or even Internet of Transportation applications, those AI techniques could be attacked, right? So we have this adversarial machine learning. And I talked about the support vector machine. How do you move the boundary, support vector machine boundary line, right? Can you apply those techniques for Internet of Transportation? Then I talked about the privacy-aware healthcare and managing one's life's activities, the privacy-aware, policy-based, quantified, not quality, I'm sorry, it's a spelling error, quantified, Q-U-A-N, F-I-E-Ds, quantified self. Okay, at the same time, right, with the development of the IoT, Internet of Things, including Internet of Transportation systems and infrastructures, security and privacy solutions are being developed, right? And I mentioned one technique that we have developed. It's mainly physics-based solution. And I gave you an example. And as driverless cars become a reality, right, more and more of the AVs, the autonomous vehicles, will use AI machine learning techniques. So the question is, how can we develop these AI solutions for detecting malware in AV autonomous vehicle systems? And how can adversarial machine learning work in AV systems? So the question is, how can, say, the stream data science or stream analytics techniques I mentioned? Because remember, in autonomous vehicles, you've got this streaming data, right? So streaming data, it's streaming, and how can you apply these AI techniques to detect malware? And what happens if these AI techniques, right, whether for cybersecurity or for, you are applying AI techniques a lot for autonomous vehicles, right, coordinate and plan and so on. What happens if those systems are attacked, those techniques? And so how can we develop appropriate adversarial machine learning techniques for AV systems? And as I mentioned, if you have driverless cars, right, which is supposed to be the future, now how can you, what happens if those systems are attacked? There you don't even have a driver to coordinate, right? And what happens if those systems, the machine learning techniques used to enable those systems are attacked? So the situation could become really quite dangerous. And then I talked about privacy-aware, policy-based data management framework for Internet of Transportation and infrastructures. Instead of a cell phone that I showed you, the smartphone, there was a vehicle. Inside the vehicle, data, the LIDAR, radar, all kinds of data being collected. So data collection, policy-aware data collection, policy-aware data storage, policy-aware data management, and policy-aware data sharing, and policy-aware data analytics. Some of the data stored in the vehicle, some data is going to be in the cloud, and how do you coordinate, right, to ensure the privacy of the individual? And finally, it's a sort of a big question mark, the last one, and I have no answer to that. We talked about trustworthy analytics with the Intel SGX, in the Intel SGX platform. Is it possible to perform trustworthy analytics efficiently so that much of the data, when so much data is coming from all directions? So how can we do trustworthy machine learning or trustworthy analytics in this environment for Internet of Transportation? And the good news is that there's numerous opportunities for substantial research. What I have done is talked about sort of data stream, data analytics, machine learning for cybersecurity, and what happens if the machine learning techniques are attacked, and some techniques for attacks for Internet of Transportation systems. You need to pull all of this together. Imagine the amount of research opportunities in this area. Okay, so I encourage you, for all of you, to look into this very exciting direction. And there are, as I said, there are so many opportunities. And finally, last but not least, I'd like to thank my colleagues. As I said, Dr. Alvaro Cardenas, top expert in cyberphysical systems. He was with us, and now he's at University of California, Santa Cruz. And then my colleagues, Dr. Murad Kantajlu, an expert in adversarial machine learning, Dr. Latifa Khan, an expert in applying machine learning for a number of applications, including cybersecurity. We have Dr. Raul Quinones, a former PhD student who has done really well. And Ms. Rhonda Walls, she's our project coordinator, and she does a lot of, supports us in a lot of aspects. And I'm sure many of you all have, worked with her. So, she just, provides a lot of support for us. So I thank all of them, because without them, this would not be possible. And I'd also like to thank our colleague, Jay Han, for his contributions, especially to our work on applying stream analytics for various applications. We did the work for NASA initially. And also Elisa Bertino from Purdue for collaborating with us on privacy-aware quantified self. And I'd also like to thank Dr. Maribel Fernandez from King's College, University of London. We are working together on access control for IoT systems. So all of these contributions have resulted in this presentation. So again, thank you very much. And I think I have taken, I was given about 55 minutes, so I'm assuming that's with questions. And I've taken probably around 46 minutes. So I think we have quite, I rushed a little bit because I didn't want to get over the time limit, because on Saturday, I gave a keynote address and I was supposed to talk for, 45 minutes, and I went over 55 minutes, and I didn't want to do that, because if we are giving a live presentation, at least the moderator of the session can show signs saying you've got 5 minutes, but here we are recording, we are doing it virtually. And so, it's hard to show signs when you have a virtual, presentation. So, but I think we'll have enough time for hopefully a few questions. And anyway, it's very disappointing that we cannot meet in person this year. Hopefully next year. I remember last year, IRI, we were all in Los Angeles 1 year ago. And 2 years ago, we were in Salt Lake City. So, IRI, community has become sort of a family to me, coming here almost every year since 2009. So it's actually my 12th year at IRI, and I believe I've come here every year since then. And so hopefully next year we can all meet in person, face-to-face conference. And again, thank you very much to the organizers for inviting me to give this keynote address. So any questions at this time? Thank you. Stop sharing. And let's see. Stop recording.